So today, inshallah, we'll continue with the same topic about the image transform. And if you remember last time, we have said that we will present three types of image transform. We have the Fourier transform, the wavelet transform, and the Hooke transform. And last time we have started by the Fourier transform, which makes a transformation from the spatial domain of the image to the frequency domain. Okay? Which means transformation from the spatial domain to the frequency domain. And due to the nature of the images, we have said that we use the discrete Fourier transform. Okay, not the Fourier transform that is used with the normal continuous functions. Here we will use the discrete Fourier transform since our input here is discrete, which is in the form of finite number of pixels. And here we have said that this discrete Fourier transform is the sample Fourier transform, and this means that it doesn't contain all of the frequencies in the spectrum, but it contains the frequencies that are enough for us to reconstruct the image again. And here we have said that the number of frequencies that we will consider here, they correspond in a certain way to the number of pixels. It's directly proportional to the number of pixels in the spatial domain. And here we have said that the image in the frequency domain has the same size as the image in the spatial. So if I have, for example, an image that has the dimension of m by n in the spatial domain, in the normal domain, if I will convert it to the frequency domain, I will have another image having the same size, which is n by n. But in this case, actually, each point in this matrix, it will give me the amplitude of a certain frequency component that we have. Right? So here we have said that for a square image of n by n, the two-dimensional discrete Fourier transform, since here actually we are dealing with finding the variation in the frequency in both directions, in the horizontal and in the vertical directions. So here we say that in the frequency domain, the component at position k, row k, and column L can be obtained by multiplying the image by this kernel, and then after that I will make a summation of this multiplication. Okay? As you can see in this kernel, we have e to the power minus j something. So this means that this is a sine plus, cosine plus j sine. Okay? And as you can see from here, the frequency of the sine and cosine functions that we are using, actually they depend on the value of k and l. They depend on the value of k and l. So like this I can get, let's say, the first harmonic, the second harmonic, the third, and so on. Right? We say that f of I and f of ij here in this expression, this represents the image in the spatial domain. Okay? And the exponential term here, this is the basis function that we have talked about. This is the function that is responsible of converting my image from the spatial to the frequency. Okay. Right. Here we say that this equation can be interpreted as the value of each point f of kl in the frequency domain is obtained by multiplying the spatial image, all of the spatial image, with the corresponding base function, then after that summing all of these results of multiplication together. Okay? Also, there is another thing that we should note here, which is that the resulting values that comes out from this Fourier transform, these are complex values. Okay? They are having real and imaginary parts. So here we say that the basis function are sine and cosine waves with increasing frequency. So how can I read this resulting, let's say, values after converting to the Fourier transform? Here actually the position of the point, which is the number of the row and the number of the column, this corresponds to the frequency. So when I say f of 0, 0, this means that this represents the DC component or the average component among all of the images that I have. Okay? This is the zero frequency in both dimensions. Okay? In the row and in the column dimension. And as the value of this, let's say, indices increases, this will give me the component that corresponds to higher frequency values. Okay? Here we say that as we have the Fourier transform, we have the inverse Fourier transform. This inverse Fourier transform, as we'll see later, is capable of restoring the image again. Okay, it's capable of restoring the image again. So what is the benefit of converting or of transforming my image from the spatial domain to the frequency domain? First of all, here we have said the filtering. Okay, filtering here means that I want to remove the noise. Okay, and this term actually is called, or this operation is called denoising. Denoising means removing the noise. Okay, as much as we can. We cannot remove the noise 100%. Okay, another, let's say we can say another benefit of doing such kind of transform is compression. Right? Okay, you can use it in order to compress the image, and in this case I will compress the image in the frequency domain. Okay? And if I want to decompress it, first of all I will decompress it in the frequency domain, then convert it to the spatial domain again. Okay? Also we can use it, for example, in normal image analysis and so on. Yes? For?
Identify the shapes.
Identify the shapes, yes, yes. Like for example in the case of the Hu transform. In the Hu transform we can use it to identify shapes, as we see later. Okay? So this is the expression for the inverse image transform. Here I will provide it with the Fourier transform image, okay, and it will restore the image back again. And here the difference, as you can see here, is in the exponential part of the basis function. Here we have a positive j instead of negative j. Right. So here we say that the Fourier transform in general is a complex function of the real frequency variables. Okay, so actually here any point, let's say f of kl, this corresponds to f of kl. I can write it, for example, a of xy or a of uv. It doesn't matter. Here what I need to say is that this is the value that is resulting from the Fourier transform. Since it's complex, but this means that it has a magnitude and phase. Okay, so it can be written like this. Okay? Here, in this case, we say that for a 2D signal, if our 2D signal, here by the 2D signal, I mean the image in the spatial domain, the original image in the spatial domain. If it is real, okay, in this case, the Fourier transform has a certain symmetry. Okay, this symmetrical, let's say, relationships actually are holding here in this case. Okay, so here, as you can see, we'll find that the magnitude. Here u and v, these are the coordinates in the frequency domain. The magnitude of AUV is equal to the magnitude of A minus U minus V. Okay? Here for the phase shift, actually, as we have said before, this phase shift, it needs to be, and here we have a negative sign. We say that phi of UV is equal to negative phi of minus U minus V. Okay? And also, so this is the thing that I want you to know from here. And we will prove it in a second. Right. Another thing here, we say that Fourier and inverse Fourier transforms, both of these two operations are linear operations. If I have, let's say, a signal like this, in which W1, W2, these are constants, and the variables here are A and B, okay, and I want to get the Fourier transform of all of this expression. So this will be equal to the Fourier transform of W1A plus the Fourier transform of W2B. Okay? And since W1 and W2, these are constant values, so actually I can take them outside the transform. So here, Fourier transform of W1A is equivalent to W1 multiplied by the Fourier transform of A. Okay? So this is the meaning of saying that this operation actually is a linear operation. Okay. Another thing that is important here is that sometimes we need to compute the energy that exists inside this image, okay? For example, to compute things like, for example, the signal to noise ratio. Okay, so I need to get the original signal power relative to the noise power. Okay? So here, in order to compute the power, I need to know how can I compute the energy and so on. So here the energy that exists in any image is simply equal to how much, as you can see from this expression. We can get it either from the spatial domain or from the frequency domain. Okay? Let's assume that this is in the spatial domain. So here what I will do is that I will square the value of the different pixels, then after that I will sum up all of these squared values together. Okay? This can give me an indication about the energy that exists inside this image. So as the intensity increases, this means that I have more energy, and vice versa. Okay? So this can be obtained like this in the spatial domain, where AMN actually here it represents the intensity of the different pixels, or I can get it from the frequency domain by getting the amplitude of the different frequency components and squaring them. Okay? So these are equivalent to each other. Another thing here that is related to the properties of the Fourier transform, assume that I have these segments A, B, and C. Okay? And we have something like this. This is in the spatial domain, or let's say the left-hand side. This is in the spatial domain, or in the time domain. And the right-hand side, this is in the frequency domain. So here we can say that C in the spatial domain, if it is equal to A convolution B, this corresponds in the frequency domain that the Fourier transform of C will be equal to the Fourier transform of A multiplied by the Fourier transform of B. Okay? Also, we have something like this, vice versa. Here, if I have a multiplication in the spatial domain, this can be interpreted in the form of a convolution in the frequency domain. For the discrete Fourier transform expressions, we find something like this, as we have said before. Yeah? It can be written in different ways. So here, this is the first formula here is for the Fourier transform. The second formula here is for the inverse Fourier transform. Okay? Where f of mn, this is the original image, and capital F of uv, this is the resulting image after the transform. Okay? And of course, here we should put in consideration that here we are dealing with 2 dimensions. Okay? The horizontal and the vertical dimension. Here we have some flow charts that shows us the different steps that we need in order to compute it. It's nice to know it. Okay? And these are the examples. So let's go to the examples that we have in the book on this part. Before going to the examples, do you have any questions here related to what we have said so far? So as we have said before, actually you have studied this kind of transforming details in the signals and systems, and now we are trying to use it for certain purpose in our course here. Okay? So what you have already studied in the form of basic concepts and so on, now we are trying to see how can we apply them in something useful. Okay? Let's go to the here, as you have seen before, here we have x is equal to 100 multiplied by the values of ones, right? So this means that here I have a vector that has 1000 elements, and all of them are having the same value. Okay? So as we have seen before, if I get the Fourier transform of this expression, it will give me just one component at 0, okay? Which is the first element in the resulting Fourier transform. So here, if I say x is equal to first Fourier transform of x, we find that the resulting value of capital X actually has this exactly the same size as the original signal. Okay, and here you will find that x, the 0 frequency here, it corresponds to the element with index 1, right? Because here the indices, as we have said before, for the MATLAB, they start from 1. This value, if I want to normalize it in order to give me an information about what is the average exactly, so I need to divide it by how much? By the number of the elements that exist in this matrix. Okay? So here it should be divided by the number of elements in X. Okay? So here, as you can see, this is the average value, which is 100. Okay? We have seen things like this one. Also, let's assume that if I have yes, to get the normalized value, which corresponds to the actual level of the signal. Type. Let's assume that I can say that this x of equal to zeros of 1000. So here we have a vector of zeros, x of, let's say, 2 to 1000. Okay. So here, what I'm trying to do here is the order of the even number index elements. Actually, I will give it the value of 100, and the remaining elements that have odd indices will be equal to 0. So in this case, what will be the frequency? This will be repeated how many times in the range of the 1000? It will be divided by 2. So actually, this will be repeated 500 times. So this means that at the frequency value of 500, I should have a peak value, right? So let's make the transform again here. We can say that x of 500. So here I need to go to the element whose index is 501, right? So we'll have something like this, okay? In order to get the normal value, first of all, I need to get the absolute, because here the absolute, since this value can have complex values, so it's better to deal with the absolute, which will give you the magnitude. Okay, divided by the number of elements here, number of elements of x. So here it will give me 50. But the amplitude was 100, right? But the amplitude here was 100. So actually here, what you will find is that for this 50, in order to obtain it, all of the values that corresponds to the levels or the frequencies other than 0, will find that their magnitude actually, it will be halved. Because actually, for any value that has a non-zero frequency, it will have its corresponding, let's say, Fourier transform will appear at the frequency f and negative f. Okay? So that at the f I will have half the amplitude, and at negative f I will have the other half of the amplitude. Understand the idea? Is it clear? So that's why here we have the value is equal to 50. Right, let's try and see. Yes. Yes, actually here when we talk about the Fourier transform, this is the frequency, this is the zero frequency, right? Okay? All the time here, if I have, for example, my original signal is a real signal, what we will have is that I will have my frequency components, they will appear in the positive frequency and in the negative frequency, and they will be exactly symmetric to each other. Okay? So for example here, if I have, let's say, at frequency f, an amplitude like this, let's call it A, at the frequency minus f, I will have amplitude A as well. Okay? If I talk here about the amplitude A that corresponds to this frequency, actually it will be equal to half the amplitude in the original signal. Okay? If I want to get the full amplitude, I need to multiply it by 2. But for the zero, actually I will have both of the two components actually that appears as symmetric, they will coincide over each other, so I will have the full amplitude. Okay? For example here I will have something like this, let's call it مثلا, I don't know, say x bar or something that corresponds to the average value. Okay? So if you remember before, we have said that if I want to get the Fourier transform of a signal that has real value, the resulting Fourier transform, it will be symmetric around the zero frequency. Okay? In our case here, for the first Fourier transform that is implemented in MATLAB, this negative part of the frequency actually is to be added at the end of the vector that will result here. So actually, if I want to transfer, or let's say transform the levels of the frequency of this signal that are having values at indices 1, 2, 3, and so on, 4, up to 1000. Okay? We have said that its corresponding frequency spectrum, it will have a frequency that has a maximum value of 500. Because 500 actually here, this is the maximum frequency that can happen here. Okay? How did I get this? If, for example, I will assume that at position 1 I have 0, at position 2 I have a maximum value, at position 3 I have a 0, at position 4 I have a maximum value, something like this. This is the maximum number of variations that I can have within this range. Like this form here, it will be repeated how many times? It will be repeated 500 times, which is half the number of the elements that I have. Okay? So here we'll find that if I will convert this in the frequency domain, I will find that from 1, here 1 it corresponds to the DC level, okay? Up to 500, this will give me one part of the spectrum, and the other part of the spectrum, it will be above 100, above 500, up to 1000. This corresponds to the negative part of the spectrum, okay? Because here we don't have negative indices, so what happened here is that the part that appears in the negative part, it was shifted to appear in the second half of the matrix that we have. It is just a question of shifting the amplitudes that we have in the frequency domain. Okay? Yeah, I hope that the main idea is clear now. Okay? I hope so. I don't know, in the digitals, in the signals and systems, did you consider the discrete Fourier transform or just the continuous Fourier transform? Continuous? Okay. So for the discrete, actually, as we have said before, it is somehow different. In the continuous, as you are treating the signal as if it is extended from negative infinity to positive infinity, right? With respect to time. But here, actually, for the discrete, I have certain number of finite values within a certain confined range, okay, which is represented by the width of the image and the height of the image. Or in this simple case, which is represented by the number of elements that exist in the vector that I want to transform. Okay? Right? So this is one thing. So here, the other thing is that, as we have seen here, the maximum number of repetitions that can happen within a range of n elements, the number of repetitions will be equal to n over 2. So this means that I will have n over 2 frequencies. Right? But here we have said that for the discrete Fourier transform, if I will make a transformation, okay, the size of the matrix that is resulting from the transformation has the same size as the original matrix, right? But here we have said that the only part that has meaning actually is half the matrix. Okay? So what about the other half? The other half corresponds to the result of the transformation that appears in the negative frequency in the normal case. Okay? So this part actually is to be put in the second half of the matrix. And we will see later maybe if we use some other. Taban, this signal, if you want to see the current situation of the signal, we'll find that, let's plot it like this, plot. Here we have x of 140. Something like this, okay? So as you can see here, it is fluctuating between 0 and 100, okay? Like this, right? Right. Let's add to this frequency, or to this signal, I will add to it another signal, but with a frequency that is equal to 250, okay? Which will be 1/4 of the the samples that I have, I will add to it 100. So the 1, 2, 3 will be the same, and the 4th I will add 100. Then 5, 6, 7 will be the same, then the 8th I will add 100, and so on. So like this I will have another signal that has a frequency of 250. Right? From where did I get this 250? I will find that this pattern, it will be repeated 250 times within the 1000 samples that I have. Okay? So how can we do this? Very simple. Here I will use the same function that we have done before, but with 4. And I will say that the new value of this element will be equal to the old value of the same element plus 100, something like this. Clear? If we plot the signal before making the transform, just to have an idea, it will be something like this. Take care of something here. We have this amplitude is 100 and this one is 200. So actually here I have levels of 100, okay? But every 4th sample here I will have a level of 200, okay? So now if we get the Fourier transform of this signal, have any question? Let's see here. So here we'll use the function of fine. خلينا ناخد ال absolute of x is equal to abs of x. خلينا الأول, let's try to plot the signal x as is, okay, and see what will happen. We will have a problem here or not. Plot of x. Okay, we didn't have a problem. Very good. So let's look at the values of x that we have. So I always prefer to use the absolute value of the result of the transform. So if the result of the transform is x, I will apply to it the absolute. So here it will give me the magnitude. Okay, just in case if I have a value that has a complex expression. Okay, so here I will make something like this. Then after that I will say find ax that is greater than 0. Okay, so here we have the ax of the values of that exist here inside this matrix that are greater than 0. They are having this indices 1, 251, 501, 751. Okay, this one corresponds to what? Corresponds to what frequency? 0. So this corresponds to the average. Okay, so this means that I have an average value for this signal. Okay, but for this one, which is 250, this actually corresponds to the frequency of 250. I will all the time subtract 1. And this one corresponds to the frequency of 500. Okay, and this one 751. This is the complement of that one. Okay, this is the complement of that one, or we can say the complex conjugate of that one. Okay, so yes.
From where we got to 500?
500 is because we have the original signal that have been with the maximum frequency that varies from 0, 100, 0, 100, and so on. Okay, so this is for the component that has the highest frequency. Okay, and this 250 and 750, this corresponds to the component that has the frequency of 250. Okay, so now let's look at the values. Just use the result of this find and put it here as indices of the matrix. So we'll have something like this. خلينا نقسمها كمان على number of elements. So like this it will be normalized. So here I will take a of x. So this will be a normalized value. So this is the DC component. Okay, this is the component that corresponds to the maximum frequency, and these two actually they correspond to the component that corresponds to what? To the frequency of 250. Okay, let's look at the values that we have here. Ax of 251. Yes? I beg pardon? Yes. تاني سؤالك؟ الفاليوز اللي احنا طلعناهم بس ده اللي هو الفاليوز اللي طلعت نتيجة الترانسفورم، نتيجة اللي احنا بنسميه الفورير ترانسفورم. Yes, yes. Because actually here, in order to see that this value actually corresponds to the actual level of the frequency, or the actual level, or let's say the amplitude of the sine signal with this frequency, okay? To get the actual amplitude, actually I need to divide it by the number of elements. This is called a normalization step. Okay? So here the signal is normalized. Let's apply it, for example, now for a figure. Let's take, for example, this figure. It is called tower.jpg. So this is the image that we will analyze now. Okay? This image actually it has an RGB components. So each level actually it will be analyzed separately. And instead of using the fast Fourier transform or FFT function, I will use the FFT2. Because in this case I will analyze it in 2 dimensions. In rows and columns. Okay? Right? In the first case that we have seen, actually we have just a vector that has just 1 dimension. So that's why I needed just the FFT. But in order to analyze a signal like this one that has 2 dimensions, rows and columns, I will use the FFT2. Okay? So here we'll find, first of all, let's start by the grayscale image. And if I will convert this image to grayscale, so that we will have just 1 layer, and we will analyze it. So this is the resulting grayscale. I have converted it using the RGB to gray, right? Then after that, we will apply, as you can see from here, this is the function that we have, xg. This is the resulting result of the transform. This is the function that we use, which is the FFT2. Okay? This is the original signal that we have, which is the image. And here 1024, 1024. Here I can expand the size of the resulting matrix. Okay, I can specify it here. If I don't put 1024, 1024, what will be the size of the xg? It will be the size of the small xg, which is 579 to 190. Okay? Fine. Now let's look at what will happen here. Control C. So now this is calculated. As you can see here, xg has this dimension. And he's saying that the type of the elements here is complex. Okay? Fine. As we have said before, it's better to use the absolute value. So we will take this computation of the magnitude and I will store it in another matrix here, xgm. So now we have the magnitude and its type is double. Okay? Fine. Then after that, now let's look at the Control C, Control V, the display, sorry. Here I am displaying, this is the result of the signal that we have created, or the result of the transform. Okay? The bright dots here, this means that these are frequency components that are having high amplitudes. Okay? The dark one here, this means that these frequency components actually have low amplitudes. How can I read this figure? How can I read this figure? Actually, here, this figure, I need to read it in 2 dimensions. If we take the horizontal dimension, this point here to the extreme left, this corresponds to the minimum frequency. Okay? And as we will go in this direction, I am going to the maximum frequency that I can attain until I reach the let's say the midpoint of this range. If I go along, if I continue in this direction, again, what will happen is that this corresponds to the frequency components with lower values. So this means that I can say that this width can be divided into 2 parts. Okay? Assume that this is the midpoint. Okay? From here to there, let's say from left to right, this corresponds to 0 frequency and this corresponds to F max. Okay? And after the F max going in this direction, what will happen is that the frequency will drop again. Okay? Same thing can be said for the vertical direction. Okay? Here, this corresponds to the zero frequency. Here, for the midpoint, let's assume that this midpoint, this is our midpoint. I will call this F max. Let's call it nu max, and this one, let's call it V max. Okay? So during this part, from 0 to V max, the frequency is increasing, and from the V max upwards, actually, the frequency is decreasing. Okay? What I will find then is that I have a symmetry around the midpoint. Okay? If I take, for example, in this, let's say, vertical direction, I take a point from here that has the same distance from V max as this point. What is the relationship between point 1 and point 2? They are having the same magnitude, but they are complex conjugate to each other. Okay? Right? This will introduce us, in this case, actually, to read the figure is not that easy. So there is a better way to organize things, okay? Which is something that's called what? FT shift. This means that I will assume that I will divide this figure into 4 quarters, like this one, okay? And I will make some sort of swapping. Okay, I will make some sort of swapping. This will be put here and this will be put here. So I will find that the midpoint here, this will correspond to the zero frequency. And as I go away from this point, the frequency will increase. Okay, so how can we do this? We have a function that is responsible for this, which is called the FT shift. So here I will take the absolute magnitude value that I have already computed before. I will apply on it this function. Okay? So this will give me something that's called XGMS. And now I will plot this XGMS. Okay? What do you expect to see here? If I will plot this figure here. The original figure was this one. Okay? After dividing this figure into the 4 quarters that we have talked about, okay, and making this kind of swapping, what do I expect to see here? The bright pixel will appear where? Here, or the bright points will appear where? In the middle, okay? And as we go away from the middle, from the center, I will find that the image will become darker, right? So let's see here. So it will be something like this. So this center point, this corresponds to the zero frequency. Okay? As we go away from it, actually, this means that the frequency will increase in both directions, in the rows and colors. If I want to go from this center point, and I want to consider the higher frequencies only in the, let's say, in the direction, in the horizontal direction. So I should go like this, in this direction, and in this direction. Okay? So as we go in both of these directions, this corresponds to the higher frequencies in the horizontal direction. As we go here vertically up and down, this corresponds that I'm going to the higher frequencies in the vertical direction. Okay? Right? And as you can see from here, as expected, I can see that this white region, which corresponds to the frequency components with high amplitudes, all of them are concentrated where? At the center. All of them are concentrated at the center. Okay? And as we go away from the center here, for the high frequency components, the amplitudes here are smooth, are low. Okay? Because, actually, if this image, as we'll see inshallah next lecture, if this image is, if we add noise to it, I will find here more white dots will appear in this dark region. More white dots here will appear in the region of high frequency. Because the noise here is characterized by having high frequency components. Okay? So like this, if I want to filter the image and I have it in, let's say, in the frequency domain like this, okay? How can I filter it? Just try to consider that here I have a certain region in this axis. Okay? Force these values to be equal to 0. Then after that, make the inverse Fourier transform. So like this, you have reduced the effect of the noise. Okay? You didn't eliminate all of the noise, but you have reduced the effect of the noise. Right? Okay? Right. So for today, we will stop here.